All right. Our next speaker is Professor Brandon Englot from the Department of Mechanical Engineering. Brandon is a recipient of both the Career and the ONR Young Investigator Award. It's a very impressive accomplishment. And the title of Brandon's talk is Intelligent Autonomous Navigation for Mobile Robots Operating in Complex Environments. Brandon?
Thanks, Henry. It's a pleasure to speak with you today. This slide gives an overview of some of our most recent active projects in autonomous navigation for mobile robots. And actually the two on the left focus on navigation problems that are especially relevant for underwater robots that have challenges obtaining complete observability of their states and their environments. They're usually plagued by very high localization uncertainty. And so they have to plan very carefully when and how they can collect relative measurements of their environment in order to stay on track and know where they are for the purpose of building accurate maps. Those are problems that are interesting and worth discussing in greater detail, but for today, I'm actually going to focus on a different problem, the one on the right. I will be giving a seminar in the ME department next Thursday where I'll talk about these first two problems in greater detail. Today, I'm going to talk to you about a problem that we recently received funding to explore through the ONR Young Investigator Program. And this focuses on safe learning and safe decision-making that could hopefully support robot navigation in the future. Although at present, we're kind of looking at this problem in a more generalized context. And the example shown on the right of this slide actually demonstrates the setting that we're thinking about pretty nicely, which is reinforcement learning, in which robots are trying to make decisions that will, maximize their reward related to whatever task they're performing. But also we're concerned about doing so in a way that manages safety and manages risk effectively. So what you see there are probability distributions describing the reward that a robot will receive in the instance that it takes these two different actions that it has the option of taking right now. One action number one, you could see has a yellow colored probability distribution. That's the distribution indicating how much reward we expect the robot to receive when it chooses action one. And the x-axis here shows you the amount of the reward. So being further to the right is a more profitable outcome for the robot. Action number two, as you can see, the gray action is bimodal. So there's some probability mass on the right showing that the robot might receive a very high reward if things go well. There's also some probability mass on the left showing that the robot might actually receive a very low reward if things don't go well. And both of these outcomes are possible. Now, one scenario to kind of map these to a realistic robot navigation problem might be a self-driving car approaching an intersection. And that self-driving car has the right of way, but it has to decide whether it wants to slow down just in case the car opposite it at the intersection doesn't obey the stop sign, right? Maybe that other car will blow through the stop sign, causing a collision hazard. So the robot has to decide whether it will take a slightly less profitable action, action one, that has this kind of nice unimodal outcome with very low risk. So you can imagine this being the outcome of me slowing down as I approach the intersection, just to be safe and make sure that I don't crash. The other action, action two, that could be me passing through at full speed, knowing that I have the right of way. There's some low probability I could get into an accident if the other car doesn't obey the stop sign, right? So these are the kind of decisions that self-driving cars and other robots might have to make on a regular basis as they approach full autonomy. And we hope robots can learn how to make these decisions and use tools like this to support their learning. And so the distributions you see here, we're actually hoping that we can employ reinforcement learning algorithms that approximate and use these distributions to make decisions. And that belongs to a class of relatively recent methods that have arisen called distributional reinforcement learning, where we no longer make decisions purely based on the expected outcome of an action. Right? The expectations are also shown in this image, actually. You can see the expected value of action one is a little bit lower than the expected value of action two. So classically, in reinforcement learning, if I expect action two will yield a higher reward, I will choose action two. even if there is this low probability outcome that might have a very, very negative reward associated with it if the car happens to crash. So rather than just reasoning about the expected outcomes of these actions, I'd like to reason about the entire probability distribution. Distributional reinforcement learning gives us tools for doing that. And so we have developed a novel algorithm that both approximates these distributions accurately. Its convergence in the first and second moments of these distributions is guaranteed. And in addition to that, we want to leverage these distributions intelligently. So given that we can approximate them accurately, we would also like to select actions that keep robots safe when they're exposed to risk. And so this is our proposed rule for selecting actions. Assuming that we can approximate these distributions accurately, we propose taking actions based on second order stochastic dominance. So what this represents, now let's look at the two actions I can choose from as X and Y. These are two different random variables describing actions that my robot can take. We're going to prefer actions that stochastically dominate others. And specifically, our proposed algorithm, which is captured in a paper that we recently submitted to the ICML conference, first authored by one of my PhD students, John Martin. And so John's idea behind this work is perhaps second order stochastic dominance is a means toward safer action selection, where all other things being equal, robots will choose riskier actions that lead to fewer crashes of the type you saw represented by the failure mode on the previous slide. So what does this really mean in practice? Well, it means trying to choose the superior gamble between X and Y, and all things being equal, choosing the less risky gamble. So assuming I have the same mean expected from choosing gamble X versus gamble Y, X is dominant over Y if it's less risky and its outcomes are less dispersed. So if a variable like X dominates another one like Y to the second order, that also implies the following, which is a little more intuitive to understand. By X dominating Y, it also means that X's payoff is expected to be greater than that of Y. The expected outcome is expected to be greater. Or if the expected outcome is equal, it is assumed that the variance of X will be lower than that of Y. So X will be a less risky action, all other things being equal. And so what we hope to introduce into reinforcement learning, specifically into this new class of methods called distributional reinforcement learning, is a preference for less risky actions. And so we explore this using kind of a simple example called the cliff walking problem, where a robot is just kind of walking around in this grid world environment. Everywhere it goes, it incurs some cost for the time that it's taking to get there. That cost is -1, a reward of -1 for all the various state transitions it makes in this environment. However, there is one catastrophic outcome that can happen, which is if the robot falls off the cliff, which is indicated by this gray region here, it receives a reward of -100. So that's the equivalent of the car crashing in the previous example. So what we would like to do is develop algorithms that allow robots to learn in an environment like this while minimizing the number of times that the robot has to fall off the cliff in order to converge toward an optimal policy. So the types of distributions that we learn, an example of what they look like is shown here on the right. So this shows you the types of distributions our algorithm converges to for the very first state the robot starts in. So the robot starts in the bottom left corner of this environment, and it has to evaluate, do I go up, left, right, or down? These are the reward distributions associated with those different actions. And one thing you can see is that going to the right by far is the least profitable action. That's the one that will send the robot flying off the cliff. And slightly breaking the tie for the best action is just going up, which results in ideally avoiding a fall off the cliff and getting to the ultimate goal in the bottom right corner of the map as quickly as possible. So we can approximate these distributions and use these distributions as tools for decision making while we're doing reinforcement learning. And we've developed a version of this problem where the rewards are adjusted a little bit so that taking a very safe path that walks away from the cliff edge is equally profitable as walking along the cliff edge itself. So we've tweaked the values of those rewards slightly so the robot does not incur any additional cost for taking a safer path. And the rewards along the edge of the cliff are also somewhat randomized. So sometimes you'll get a higher reward, sometimes you'll get a slightly lower reward walking on the edge of the cliff. So what does our algorithm look like in practice when it is compared against other algorithms that are less cognizant of risk? So we've compared our algorithm here, which is shown in green, which uses Wasserstein gradient flows to approximate these return distributions, and uses second order stochastic dominance to select actions, against algorithms that instead select actions using CVAR for different risk thresholds. So what you see here is our algorithm is converging a little more quickly to the optimal reward. One reason is because it's doing a little bit less falling off the cliff. It ends up choosing safer actions. It has an aversion to risk. All of these algorithms end up converging to the optimal policy, more or less, but the question is, how do they do so? So our algorithm, the intent is that it will also get to the optimal policy like all the others, but it will do so by exposing the agent to a little bit less risk along the way. And then here's another slide just showing you the number of times the robot actually falls off the cliff in the course of learning. And again, our algorithm is exposed to a little bit less risk in the course of converging to an optimal solution. And you can see it falls off the cliff fewer times. And just to wrap up here, what we're thinking about in the future is how this algorithm can be extended and employed on real robots that have to make similar types of decisions, that have to learn in the presence of risk, and have to choose actions that might have failure modes that could lead to dangerous outcomes. Now, of course, for a real robot, it's still unacceptable to fall off the cliff 20 times rather than 40 times. So we're also thinking about what the pipeline might look like for transfer learning, where we can begin learning in simulation, expose the robot to risk, and then perhaps gradually introduce our learned policy onto robot hardware once we trust it a bit more and its outcomes are a bit more predictable. Thanks for listening, and I'm happy to take any questions.
Okay, thanks, Brandon. Exciting work. I don't see any questions submitted. Let me just ask you one question anyway then. Certainly in your algorithm, right, you talked about basically the risk factors for the robots. But how about the ethical considerations? For example, if you have a car, right, autopilot and driven by itself onto a road, and there are two possible scenarios. One is hitting a child of 10 years old, and the other is an adult or elderly person of 80 years old. And how would you, basically there's only just one outcome, how would you consider those scenarios in your algorithm in terms of
that's a good question.
Or totally avoid a crash. But once again, if there's no way you can avoid the accident from taking place.
Yeah, so there are lots of interesting dilemmas that come up like that when you think about risk that enters into the decision making for autonomous vehicles, and people like to present the scenario: what if you have to choose between one failure mode and another failure mode? One challenge in an approach like this that comes back to the human designer, right, is that it is humans ultimately that craft the reward functions, that govern an autonomous robot's operation. So I think that, that's one area, in addition to reward functions, all the different, aspects governing how autonomous agents make decisions in the real world. We as a society, I think, have to, our understanding of all the contexts in which we trust autonomous vehicles to operate has to evolve a bit, I think, before we can trust a piece of code or a human crafted reward function to govern those kind of decisions. For now, though, that I would say is the limitation. The limitation lies in the fact that this reward function is crafted by a human designer, and it might not capture all of the different sources of risk appropriately. So those have to be subject really to scrutiny before something like this could be employed in the real world.
Okay, I see a lot of questions submitted in the online platform, but in the interest of time, let me take just one question. My apologies. And so this question is about what is the possibility for mobile robots in a public setting?
Well, we already are getting there, right? If you think about the Tesla autopilot and the fact that anyone who buys a Tesla has access to that autopilot feature and has the opportunity to use it and potentially abuse it we already are seeing mobile robots operating in public settings. And I think the emphasis here is on a path to increased safety. You know, what in particular, we would like to use techniques like this to really understand the corner cases, the things that come up very, very rarely, even in real driving, right? Where you may have to drive thousands of hours before some type of very low probability event occurs. And we hope, you know, through some combination of looking at those events in simulation and with real hardware, you could capture those things in these types of distributions and hopefully manage risk and avoid those types of corner cases.